Again, the topic is spectrophotometry. Photometry. And let's say, good evening. Let's say in the lab we do an experiment. For example, we want to measure the concentration of ATP in a sample. ATP concentration in a sample. And we know that we can do that using the Beer-Lambert law, where we have absorbance equals the concentration of our substance times the path length of our little cuvette times the extinction coefficient for this particular substance at a certain wavelength. And we also know that ATP absorbs at around, so ATP absorbance is quite high when we use light with the wavelength of 260 nanometers. So that would be in the UV range. Okay, so now we have our little sample. We put that in a cuvette, measure it at 260 nanometer, and we find that our ATP sample has an absorbance of 0.25. What's the unit for absorbance? There is no unit exactly. So we have an absorbance of 0.25. Is that good or bad? It's bad. Why?
Because it's much less than 1.
Aha, it's much less than 1. I told you last on Monday that 1 is sort of a critical limit with absorbance. Actually, what I meant to say, probably didn't make it very clear, anything above 1 is bad. But we are below 1, so absorbance of 0.25, okay. Can deal with that. Yeah? The spec can't deal with anything that's higher than 1. Lower than 1, not a problem. So 0.25 is okay. So, can anyone tell me what the concentration of this ATP solution is? Any ideas? Can anyone tell me? Shall I let you into a secret? I can't either. What's missing? Sorry? The path length? Oh, well, I can easily use that because it's usually, unless something really weird happens, the path length is always 1 centimeter. We can give that. If nothing else is stated, let's assume it's 1 centimeter. What's missing? The extinction coefficient. This guy here is missing. And I told you that the extinction coefficient depends, of course, on the wavelength. It also depends on the temperature. It also depends on the pH of the solution. It depends on a lot of things, right? Now, I could try to figure out what this extinction coefficient is by just try to Google it. and see if anything is known about the extinction coefficient of ATP. And the answer is yes, up to a certain point, because the conditions might be slightly different. Yeah? So this extinction coefficient is missing. But I tell you what, my supervisor really needs to know what the concentration of this ATP solution is. What can I do? Any creative ideas? What can I do? Yes?
Concentration curve.
Make a loud?
Concentration curve.
A concentration curve. I like your idea. What is a concentration curve? You're basically now my supervisor. You tell me what you mean.
Basically, you get like a range of known concentrations and measure the absorbance of each one. So say you could start from like just 0.1 and then go all the way to 1, as long as you know what the concentration is, and then measure the absorbance of each of those and make a curve.
Make a curve. You are a genius. Right? You are an absolute genius. Because what you just described is exactly the procedure that I will do. I do, and usually people don't call it a concentration curve, they usually call it a standard curve. Tomatoes, it's the same thing. Yeah? A standard curve. Now, what we do with a standard curve is actually we take some concentrations of ATP as close to the conditions as we have in our sample here, and measure the absorbance of these known concentrations. And as you absolutely rightly said, sorry, what was your name? Gokul. What Gokul absolutely rightly said was, what we just simply do is we take certain concentrations of ATP that we can make up of ATP, and we measure the absorbance of these things. And what we get then would be ideally something like that. So we have our concentration here, and we have the absorbance here. So that would be then our sort of standard curve, very roughly sketched. This would be our standard curve. From this standard curve, we then can say, right, we have a curve, well, looks a little bit like a curve, but the intention was a straight line, actually. Never mind, it's too early. But from this standard curve, we then can actually say, right, let's use our unknown concentration, our unknown sample, let's measure the absorbance, which we just did, it's 0.25, and from this, we just simply read it off here. So if that is 0.25, we read it off here, and that corresponds to this concentration. Does that make sense to you? Yeah? You see what a standard curve actually does. It's extremely useful because it can help us, even if we don't have the low-flying pens today, even if we don't have an extinction coefficient. Right, so let's do that. Right? And we measure We make up different concentrations. So, for example, we use solution in the first place where we have no ATP in it. So no ATP. What would you expect is the absorbance of a solution that has no ATP in it? 100? What 100? Why 100? Is there anything in it that would absorb the light? No. So if there's nothing in it, the absorbance should be 0, shouldn't it? Make sense? Sorry? You were thinking the other way around. You were thinking in transmission. Yeah. Valid point. But the absorbance in this case would be 0. Now we have a solution where we have 1, and in this case 1 micromolar solution. And we measure an absorbance of 0.0, should I say? 0.015. 4 micromolar, we have 0.06. 8 micromolar, we have 0.12. 12 micromolar, it is 0.18. 20 micromolar, we have 0.3, and we have 25 micromolar, we have 0.375. Did that get on the board? Yes. Okay. Are our readings all right? Are our readings all right? Is there a dodgy reading in it? Is there anything above 1? No. So, hallelujah, it's okay. Yeah? So we don't have to worry. If it goes over 1, what did we say we need to do in this case? Dilution, exactly. We have to dilute it so that it goes below 1. Absolutely right. So, under normal circumstances, I would ask you now to draw this graph. I forgot to ask you last time to bring in some graph paper. But what you could do is roughly try to sketch this graph, what this graph would look like, okay? Can you do that? I'll give you 5-6 minutes for that. So here's the concentration. And here is the absorbance. Not terribly exciting, but we actually need that. And it is fairly accurate. Okay? Any questions? Really trivial, the whole thing. But we have to do the standard curve first, and that is where a lot of people have problems. Okay, so should be able to read from a standard curve. We do a second measurement of another sample, and in our second measurement we get an absorbance, and I write this here. Absorbance is 0.45. 0.45. what actually is the concentration? Can you read that? Sorry? You have to extrapolate the line. So this is what you're basically saying. Yeah? Extrapolate the line. Are you allowed to do that? No, why not? It might change up there. So it could be that it goes like that now. Yeah? Could be that it goes like that now. So the important message is, if your measurement is outside your standard curve, you can't use it. What can you do? Sorry? Do the graph again. Oh, I don't have time for that now. What could you do if your absorbance is too high, Coco? Dilute it again. Yeah, you could dilute your sample. So you could take, for example, 100 microliter of this plus 900 microliter of your buffer, bless you. What would be the absorbance that you expect from this one? How much have you diluted it? You've got 100 microliter of your sample now in a total volume of 1 milliliter, exactly. So that's 1 milliliter. So you've got 100 in 1,000. There would be a dilution of 1 in 10, exactly. So 1 in 10 dilution of this. What do you think will happen to the absorbance? It will be just 1/10 of the original absorbance. So in this case, we would expect an absorbance of 0.045. Yeah? But I need to remember that I've diluted it later on when I report it. So 0.045, that's probably somewhere here. Go down. And that's probably around 3 micromolar. That was my 1 in 10 dilution. 3 micromolar of 10-fold diluted. So what was the original concentration? It was 30 micromolar. So original was 30 micromolar. I couldn't do the 30 because that would have been too high. So if the absorbance is outside my range, diluted, let's see what we get. But don't forget that we've diluted it in the first place. Yeah? Make sense? Actually, for our unknown sample that we had, we got an absorbance of 0.25. And we said that is equivalent to probably 17.5 micromolar. Tell you what, shall we do a little bit of a reality check? Is it possible that 17.5 micromolar give us an absorbance of 0.25? Is that possible from our data? Let's have a look. These are our data. And we said we have an absorbance of 0.25. So that would be somewhere in between here. 0.25. So it's between 0.18 and 0.3. Right? What is the corresponding concentration? Well, it is between 12 and 20 micromolar. So we said it's 17.5 micromolar. Is this possible? The answer is yes. Yeah? If I had read, for example, 0.25 is equivalent to a concentration of 175 micromolar. Had I done that, I would immediately see there's an error. There's something not right. 0.25, I would expect something between 12 and 20, and yet I got 175. I know that there's somewhere a mistake. Probably because I forgot a dilution or added a dilution or something like that. Yeah? So these reality checks are incredibly important, and I will pester you in future with these reality checks. Make sure that the data actually make sense. It's a little bit like with the units. When somebody calculated the diameter of an E. coli cell, and after about half an hour calculating, they came up with, oh, an E. coli cell has a diameter of 0.5 meters. And you think, if it is that big, then I would assume that occasionally I have bumped into an E. coli cell. So my first question was, have you ever seen an E. coli cell on the street? No. Would you expect to see an E. coli cell that has a diameter of 0.5 meters? Well, it turned out that the student didn't have any concept of what 0.5 meters are. It's a little bit like in Rain Man, where in the film where the guy gets asked, how much does chocolate cost? 10p. How much does a car cost? 10p. Things like that. But you see, these reality checks are absolutely essential. Oh, by the way, this happened to a French minister recently. Have you read about that? He was asked, it was sort of a check, how much are the politicians in touch with real life? And he was asked, how much does a chocolate croissant actually cost? And it's probably €1.50 or something like that. And he said, actually, I think it was, he said 10 cents or something. So that shows something about some French politicians. I don't want to generalize that. And I don't have a go at French here. So if you are French, that wasn't any nationalistic comments. So in this session, you should have seen how useful standard curves are, how important they are, how you can analyze them with Excel, how you can add a trend line very easily, and also how you then can convert the unknown substance with the help of a standard curve into a meaningful concentration. Does it make sense? You now should be able really to completely do the spectrophotometry quiz. And since you don't have anything else to do today, my advice would be give it a go. Okay? I shall see you on Monday.